Okay, Bismillahirrahmanirrahim. Assalamu alaikum. And this is our online lecture number 4, and we will cover lecture number 8 of written handwritten notes in this lecture. Okay, what this lecture covers Article 2.6, other logic operations. So far, we have covered and, or, and not operations of binary variables. So here it is stated that it was stated previously that there are 2 raised to power 2n functions of n binary variables. For two variables n is equal to 2, there are 2 raised to power 2 or 2 raised to power 4 or 16 possible Boolean functions. So if we have two variables, there are 2 raised to power 4 or 2 raised to power 2n, 16 possible functions possible. Okay. Therefore, and or functions are only two of the possible 16 functions of the two binary variables. So far, we have covered only and or operations. So we will see some other operations, maybe 14 other operations which are possible, and the truth table of these functions are given on next page. So these are the 16 possible operations or of possible with logic operations possible with two variables. First one is f is equal to 0. 0 means you can give 0 logic to input and it will remain 0, binary constant 0 or null. Okay. Next one is and. We already know what is an and, x and y. It gives an output 1 when both the variables are 1. X y bar means inhibition. It means x but not y. X will be 1, y will be 0. F3 is equal to x. The input x is given, transfer x bar y is another inhibition which means y but not x. Y will be 1 and x will be 0. Then f5 is y. F5 is y just like f3 is x. Fy is y means you can give y input to any and gate input. Then exclusive or xy bar plus x bar y. Basically this function gives a one output when both x and y are different. X is 1, y is 0 or x is 0, y is 1. It gives a one output. When both x and y are same, it will give you a 0 output. X plus y is OR. We already know what a OR function is. It gives a one output when either one of the input or both of the inputs are 1. X plus y bar is NOR, which is opposite of OR function. You simply add a NOT gate after the OR gate, you get a NOT gate. Equivalence, F9 is equivalence. F9 is opposite of exclusive OR. Basically, it gives a one output when both x and y are equal. Both x and y are 0 or both x and y are 1. It gives a one output. F10 is y bar complement of y. F12 is complement of x. F11 is x plus y bar implication, just like x bar plus y. X plus y bar and x bar plus y, both of them are implication. X complement is the complement of x. You simply put a NOT gate after x. And F14 is xy complement or NAND gate basically. NAND gate is the opposite of AND gate. You simply add a NOT gate after a AND gate and you get a NAND gate. And F15 is 1. F15 is 1 just like the first function you give F0 is equal to 0. You give 0 input to a function or gate input. You can also give one input high input to a gate input, which is identity. So here he has actually written two variables x and y and f naught to f15, the 16 possible functions which we have stated here. He has made the truth table of all of them. For example, f naught is 0. 0 meaning it will remain 0 always. And f15 is 1, it will remain 1 always. So f0 will remain 0 always. F15 will remain 1 always. And then you can see the truth table of all. For example, f1 is xy and f1 is xy and this is AND operation. When both the inputs are 1, it will give 1 output, otherwise it will give 0 output. And similarly, you can see or, and for example, you can say f6 is xy bar x bar y. F6 is F5, this is F6. When X and Y are different, it is giving a 1 output, and when X and Y are same, it is giving a 0 output. And equivalence, for example, equivalence, this one, F9, when X and Y are same, X and Y both are 1 and both are 0, it is giving a 1 output, F9. This is F9. When X and Y are both 0, it is giving a 1 output. When X and Y are both 1, it is giving a 1 output. Otherwise, when X and Y are different, it is giving a 0 output. So similarly, you can see the truth table of all the 16 operations. These are the logic operations which are possible. Digital logic gates, we have seen the first three gates already: AND gate, OR gate, and NOT gate. We have already covered that. And buffer gate basically simply gives x, f is equal to x. Whatever is input is transferred at the output. F is equal to x. So buffer gate does nothing. It doesn't do anything. It simply transfer input to the output. NAND gate is the opposite of AND gate. Basically, after AND gate, you put a inverter, or there is a truth table of NAND gate. NAND gate does the opposite of AND gate. Basically, AND gate gives you one input when both of the inputs variable are one, whereas NAND gate gives you zero output when both are inputs are one, and it gives you one output at when either one of the input is one or both of them are zero. So this is NAND gate. This is NOR gate. NOR gate also does the opposite of OR gate. You simply put a NOT gate after OR gate, and you get an OR gate. And the truth table of NOR is opposite of OR. Whatever OR gate does, whenever OR gate give you one input, NOR will give you zero output. And whenever OR gate will give you one output, it will give you zero output. For when OR gate gives you one, it will NOR will give zero. When OR gate will you gives you zero, NOR gate gives you one. And this is exclusive OR, which is X Y bar X bar Y, which we have already discussed here. This is exclusive OR. This is the gate of exclusive OR. And then last gate is exclusive NOR or equivalence, which is exclusive or equivalence, which is this function. Exclusive or equivalence, which is this function xy or xy bar. So these are some gates. These are the truth tables of NAND, NOR, XOR, exclusive OR, and exclusive NOR. Okay, then we go to Article 2.8. What is integrated circuits? Digital circuits are constructed with integrated circuits. What is an integrated circuit? Basically, a small IC chip of silicon semiconductor crystal, and it has electronic gates or components inside the chip. So gates are interconnected inside the chip to form the required circuit. You probably have used AND gate or other gates in your lab, and you might have seen a chip with 16 pins having four gates inside the chip. So that is the example of a integrated circuit. So there are level of integration. There are four levels of integration. One is small scale integration. Second is medium scale integration. Third is large scale integration, and fourth one is the very large scale integration. What is the difference between these four levels of integrations? Small scale integration will have usually fewer than 10 gates inside the chip, just like the chip you have used in your lab. And medium scale integration has 10 to 100 gates inside a single package, and the large scale integration has 100 to few thousand gates inside the chip, and very large scale have many thousands of gates inside the single package. Example of small scale integration is the chips which you have used in your lab, which have four gates inside the chip: AND gate or OR gate or NOT gate. So small scale integration are those chips. And what are the medium scale integration? Medium scale integrations are decoders or adders or multiplexers. These are the chips which are included in medium scale integration. Large scale integration are examples are processors or memory chips, which are large scale integration. examples. And very large scale integrations are memory arrays and complex microcomputers. And very large scale integration has revolutionized the computer digital system and technology. Because of VLSI or very large scale integration, we are able to make very small size electronic devices or electronic computers. Digital logic families, apart from the digital integrated circuits, the classification of integration, there are some other classification like the specific circuit technology to which they belong. So there are basically four possible circuit families of integrated circuits, digital integrated circuit. TTL is transistor logic, ECL is emitter coupled logic, and MOS is metal oxide semiconductor, and CMOS is complementary metal oxide semiconductor. These four classes are thoroughly investigated in a course which is called Digital Electronics, which you will probably study in this degree. And these are the classes. Basically, these are the technique by which your gates are fabricated inside your chip. These are the four electronic families, digital electronic families, or these are the circuit technologies which are used to make your IC chip or integrated circuit. There are three things written here about the above families. Emitter coupled logic ECL provide the highest speed among all above. MOS metal oxide semiconductor is suitable for circuit that need high component density. When you need high component density, means you want a very small size component with very large number of gates. So then you will use metal oxide semiconductor, and CMOS is preferred in system requiring low power consumption. CMOS, the power consumption of CMOS is very low. So if you require very low power consumption, then you will use CMOS. This is the positive and negative logic. Basically, positive logic means this is written positive logic. Positive logic is the symbol. This is a symbol of positive logic. So in positive logic, you represent 1 by logic high. Logic high means, or you can say logic high means logic 1, and logic low means logic 0. This is positive logic. And in negative logic, logic high means logic 0, and logic low means logic 1. This is negative logic. So these are the some techniques by which you can give inputs to a logic gate. Mostly we use positive logic in our labs. So this is the end of chapter number 2, and you can do problem 2.1 to problem 2.18 of the exercise of chapter 2, and all of these problems are included in course. You can ask any confusion among these problems in your online lecture or in our on-campus lectures. So problem 2.1 to problem 2.18 are included in our course. Okay, this was the lecture number 4 of the online lecture, or lecture number 8 of my handwritten notes. So here we will end our lecture. You can ask any queries or any confusions in our live session on Thursday. Thank you. Allah Hafiz.